Earth's heavy metals result of supernova explosion, research reveals that gold on your ring finger is stellar, and not just in a complimentary way. In a finding that may overthrow our understanding of where Earth's heavy elements such as gold and platinum come from, new research by a University of Guelph physicist suggests that most of them were spewed from a largely overlooked kind of star explosion far away in space and time from our planet. Some 80% of the heavy elements in the universe likely formed in collapsars, a rare but heavy element-rich form of supernova explosion from the gravitational collapse of old, massive stars typically 30 times as weighty as our Sun, said physics professor Daniel Siegel. That finding overturns the widely held belief that these elements mostly come from collisions between neutron stars or between a neutron star and a black hole, said Siegel. His paper co-authored with Columbia University colleagues appears today in the journal Nature. Using supercomputers, the trio simulated the dynamics of collapsars, or old stars whose gravity causes them to implode and form black holes. Under their model, massive, rapidly spinning collapsars eject heavy elements whose amounts and distribution are astonishingly similar to what we observe in our solar system, said Siegel. He joined U of G this month and is also appointed to the Perimeter Institute for Theoretical Physics, in Waterloo, ONT. Most of the elements found in nature were created in nuclear reactions in stars and ultimately expelled in huge stellar explosions. Heavy elements found on Earth and elsewhere in the universe from long-ago explosions range from gold and platinum, to uranium and plutonium used in nuclear reactors, to more exotic chemical elements such as neodymium found in consumer items such as electronics. Until now, scientists thought that these elements were cooked up mostly in stellar smash-ups involving neutron stars or black holes, as in a collision of two neutron stars observed by Earth-bound detectors that made headlines in 2017. Ironically, said Siegel, his team began working to understand the physics of that merger before their simulations pointed toward collapsars as a heavy element birth chamber. Our research on neutron star mergers has led us to believe that the birth of black holes in a very different type of stellar explosion might produce even more gold than neutron star mergers. What collapsars lack in frequency, they make up for in generation of heavy elements, said Siegel. Collapsars also produce intense flashes of gamma rays. 80% of these heavy elements we see should come from collapsars. Collapsars are fairly rare in occurrences of supernovae, even more rare than neutron star mergers, but the amount of material that they eject into space is much higher than that from neutron star mergers. The team now hopes to see its theoretical model validated by observations. Siegel said infrared instruments such as those on the James Webb Space Telescope, set for launch in 2021, should be able to detect telltale radiation pointing to heavy elements from a collapsar in a far-distant galaxy. That would be a clear signature, he said, adding that astronomers might also detect evidence of collapsars by looking at amounts and distribution of heavy element S in other stars across our Milky Way galaxy. Siegel said this research may yield clues about how our galaxy began. Trying to nail down where heavy elements come from may help us understand how the galaxy was chemically assembled and how the galaxy formed. This may actually help solve some big questions in cosmology, as heavy elements are a nice tracer. This year marks the 150th anniversary of Dmitry Mendeleev's creation of the periodic table of the chemical elements. Since then, scientists have added many more elements to the periodic table, a staple of science textbooks and classrooms worldwide. Referring to the Russian chemist, Siegel said, "We know many more elements that he didn't." What's fascinating and surprising is that, after 150 years of studying the fundamental building blocks of nature, we still don't quite understand how the universe creates a big fraction of the elements in the periodic table. Origin of life, a prebiotic route to DNA, the hereditary material, may have appeared on Earth earlier than has been assumed hitherto. Ludwig Maximilians Universität (LMU) in Munich, chemists led by Oliver Trapp show that a simple reaction pathway could have given rise to DNA subunits on the early Earth. How were the building blocks of life first formed on the early Earth? As yet, only partially satisfactory answers to this question are available. However, one thing is clear: the process of biological evolution that has given rise to the diversity of life on our planet must have been preceded by a phase of chemical evolution. During this prebiotic stage, the first polymeric molecules capable of storing information and reproducing themselves were randomly assembled from organic precursors that were available on the early Earth. The most efficient replicators subsequently evolved into the macromolecular informational nucleic acids, DNA and RNA, that became the basis for all forms of life on our planet. For billions of years, DNA has been the primary carrier of hereditary information in biological organisms. DNA strands are made up of 4 types of chemical subunits, and the genetic information it contains is encoded in the linear sequence of these nucleosides. Moreover, the 4 subunits comprise 2 complementary pairs. Interactions between 2 strands with complementary sequences are responsible for the formation of the famous double helix, and play a crucial role in DNA replication. RNA also has vital functions in the replication of DNA and in the translation of nucleotide sequences into proteins. Which of these 2 types of nucleic acid came first? The unanimous answer to that question up to now was RNA. Plausible models that explain how RNA molecules could have been synthesized from precursor compounds in prebiotic settings were first proposed decades ago, and have since received substantial experimental support. Moreover, its conformational versatility allows RNA both to store information and to act as a catalyst. These insights have led to the idea of an RNA world that preceded the emergence of DNA, which is now well established among specialists. How then were the first DNA subunits synthesized? The generally accepted view is that this process was catalyzed by an enzyme, a comparatively complex biomolecule whose emergence would have required millions of years of evolution. But now a team of chemists led by LMU's Professor Oliver Trapp has proposed a much more direct mechanism for the synthesis of DNA subunits from organic compounds that would have been present in a prebiotic environment. The reaction pathway is relatively simple, says Trapp, which suggests it could well have been realized in a prebiotic setting. For example, it does not require variations in reaction parameters, such as temperature. In Trapp's experiments, the necessary ingredients are water, a mildly alkaline pH and temperatures of between 40 and 70 degrees Celsius. Under such conditions, adequately high reaction rates and product yields are achieved, with high selectivity and correct stereochemistry. Each of the nucleoside subunits found in DNA is made up of a nitrogen-containing base and a sugar called deoxyribose. Up to now, it was thought that deoxynucleosides could only be synthesized under prebiotic conditions by directly coupling these 2 preformed components together. But no plausible non-enzymatic mechanism for such a step had ever been proposed. The essential feature of the new pathway, as Trapp explains, is that the sugar is not linked to the base in a single step. Instead, it is built up on the preformed base by a short sequence of reaction steps involving simple organic molecules such as acetaldehyde and glyceraldehyde. In addition, the LMU researchers have identified a second family of possible precursors of DNA in which the deoxyribose moiety is replaced by a different sugar. According to the authors of the study, these results suggest that the earliest DNA molecules could have appeared in parallel with RNA, some 4 billion years ago. This would mean that DNA molecules emerged around 400 million years earlier than previously thought.